Have you ever wondered how safe driving cars are able to distinguish where the road starts from and where it ends, and how it is able to actually find out like which part is the road and which part is not? That's what we call road segmentation in computer vision. My name is Daniel Bjiringiro, and I'll be walking you through how computer vision models are able to process segmentation and be able to figure out which part in the vision, in the picture, is the road or not. So to a normal human, if I give you this image, the image on my on my left, the input image, you can easily map out which part makes up the road and which one does not. But for computer vision models, they only understand bits, zeros and ones, so it can't easily figure out it can't easily figure out semantically that this part belongs to the road and this part does not. So we have to provide the image in a way that the model understands. So in the image, we kind of distinguish the pixels, stating that these pixels, which are marked yellow, make up the road, and everything else is the background. So focus on the pixels which are made of yellow. In the next segment, I'll be walking you through a project with all the code in PyTorch of how to train a model to be able to do road segmentation. So we start by importing the libraries that we will need to use in our program. So we have some libraries which are from Torch, some from Torch Vision, and we know have uh, normal code utilities that we're going to use as we go along our project. So second thing that we'll do is to get the data set. So the data set was taken from cargo, it was made by someone else. So I just took it from there. It was taken from the Kitty Road dataset. So uh, if you want to see the original images, that's where you can reference them from. But like this dataset has a specific structure. So we have like two folders from the dataset. We have a training folder and a testing one. So the training folder has also two folders inside. It has an image, and then it has the ground truth image. So I think you understand the difference as we go through. But then basically the images contain input, the input images, the ones that may be the raw images, and then the ground truth corresponds the contains the corresponding image which has been pixelated into three categories. So the first category is rows, the other one is other obstacles, and yeah, so it contains a version which a machine would more easily understand than the raw image. So we also here we are checking for the how big is our data set. So we have 231 training examples, 28 validation examples, and 30 testing examples. So we're now going to define a custom torch dataset definition since we have like the dataset locally. So what we basically do, so this class is inheriting from the torch dataset, and then what we basically do is that we take a folder, and then we sort through all the image parts, and then we get the target size of the image that we want, the height and the width. And then we also implement the length function and the get item. So the get item, what we basically do, we want to have like a tuple. So what we first take, we take the image part itself, and then we now find the corresponding mask path from the ground truth folder. And then after we do that, we read the images and then we normalize it. So we divide the pixels by 255, and then the road label now. So like we have three colors. So like magenta in the images represent the road part of the road part of the image. So we're not just taking the road label and then we're now binarizing by taking that mask. We're now checking if a pixel is equal to the road label, and then if that's it, then it's 1, else it will be 0. And then we kind of now create like our mask image. So we also do some image operations to make our data set more robust. Like some of the images are randomly flipped horizontally. So if random gives us more than 0.5, we flip the image horizontally and the mask horizontally, and then we now resize them so that they match the target size that we have. And then we now retain the type of the image and the mask. So the target size was set here. So we have an image size of 128, so 128 width and 128 height. So here we initialize the road segmentation train data directory. So, and then after that we now split the dataset into a train, validation, and test set. Then we load the dataset. So here we're now testing to see how the batching operations are working. So here we just took a single batch from the train model. So you can see that we have 32 images which have 3 channels, and each of them is 128 height and 128 width. So the images are square. So we now created a simple function to help us display a road image and the corresponding road mask. So if we take like this image, like we can see that the mask is now showing us the corresponding part in the image, which corresponds to what? Which corresponds to the road. So the model we're going to use is VGG F16, but then we are now going to modify the architecture a little. So we're now making it a fully connected neural network. So we start by getting the model from Torch models, where we get VGG16, then we get the weights, and then we now from the encoder we take the block 3 pool, the block 4 pool, and block 5 pool, and then we do some operations in the decoder. We concatenate, we upsample, and then we apply an activation function, sigmoid. And then for the forward operation, we run through the encoder and the decoder, and then we upsample to match the input size, and then we retain the image. So here we're initializing the model, and then we're running the code on a GPU device for fast, to ensure that we're able to train our model as quickly as we can. Here we're just printing the model to see what's in it. So here we're now going to train our model. We define the criteria, the optimizer, and then the metric that we're using. So here we are defining the training group. So for every epoch, we just go through the train loader, we get the images, and then we optimize output, and then we calculate the training loss. Then we now validate. So we now go through the images and see what we are predicting and see the validation loss, and then we are also going to kind of be showing how the model is improving by visualizing like the model prediction over time. So when we start in our first epoch, you can see that we have a very high loss, and our metric is very low. We have 0.6. So this is the raw image, and then this is the true mask for the road. But as you can see, the predicted mask is very way off. This is very different from this. So, but then as we go to the second epoch, we can see that our metric is increasing, and then the loss is also decreasing. So yeah, so over time, when we reach around, so you can see that it's kind of now adapting to the shape of the true mask. Around epoch 11, we're now at 0.85. We started from 0.6, so this is a very huge increase. And you can see that the loss is now 0.09 when we started from 0.4. So over time the model becomes better to the extent where you can see that now, like, though it's not like perfect, but like it's now adapting to the general shape of the road, which is way better than like how it initially started. So yeah, so you can see that the model was able to improve cross training, train it for over 100 epochs. So say we went from 86, 88, 87, so we are hovering around 86, 87, 88. Then yeah, here you get 89. So by the last epoch, let's go to the last one, 100th. Yeah, so the last epoch ends at 89, and then you can see that the loss has significantly decreased, and then that the prediction is a little bit better than what we started with. So the model was able to increase its accuracy over time. So after that, we evaluate the model now on our test images. So we just go through the test loader, and we can see that now our predictions, so the true mask and the predicted mask. So you can see that the general shape is there. So our model has now become very better at predicting, like segmenting the road from other parts of the images. So yeah, so like this one, you can see that it's not 100%, but the general shape is there also. Same for this one also. Yeah, so we have about 31 test images, and we ran through all of them. You can see that though it's not perfect, the general shape is there, and then the model has improved in its ability to recognize image shape and image and road patterns. Yeah, so this is basically how these are the building blocks of a road segmentation model. And road segmentation models are very crucial for self-driving cars, because if the car is not able to determine where the road is, then it's not able to travel. So this is a crucial building block of self-driving car technologies. Thank you all.